Okay. Get the lights adjusted. Welcome to Eclipse Day, or Lecture 24 here in Engineering 102. We are down to the wire, folks. And when I say down to the wire, we have this week and next, and we are done. We don't have a final exam in here, and I'll do you one better. We are not going to have an in-person class next Wednesday, okay? Mainly because I'm going to be out of town at a conference. So I'll probably pre-record something, and that pre-recording will largely be just some clarifications and hints and tips and tricks and all that jazz for the final assembly. I'll also probably cover in that like a very, very quick review on if you wanted to take that assembly and print it using 3D printing, how do you do it? And it's really simple. All you do is just save it as an STL file and then upload the STL file into a software like MakerBot or something, and then it'll be printed. That's basically it. So it's really all there is to it. The big thing about 3D printing is ensuring that your parts are to scale, which is something I certainly know that you all know how to do by now after everything that we've done in this course. So that part's pretty straightforward. Okay. Now, right now, what I'm passing around is a hard copy of the virtual lecture that we had last week because of the tornado. Okay. So this is basically the handout that I was following in that video on how to create the wheel. Okay. So this is the handout on that. I do, if you remember last week, I did not have like an assignment for you, a prepared assignment, because the idea is that we would work on the assembly. The assembly has a total of 4 parts, that we're going to use 5 times, okay? What I'm going to say is next week, I'm going to give you the formal assembly assignment, okay? On Monday of next week, we are going to start putting this together. So what I'll tell you is next week, it would be a good idea for you if you had the 4 parts created, okay? We've already done 2 of them together, so I would say if you have not created them all by Monday, like I'm just saying I would have them created, because what I'll do on Monday is sort of show you how to piece everything together, okay? So that's a nice goal for you. If you have the 4 parts created, then the assembly process in total will probably take no more than an hour or so, and most of that hour will be creating the drawing. The actual process of assembling it together can be done in a matter of minutes. Okay? It's a really straightforward process. All right. Does anybody have any questions about where we're headed so far? Okay. Now, for this week, okay, I don't have an assignment for you today. I am going to have a short assignment for you this week on stress analysis. So my thought is, while you're working on your assembly in the background, we'll take sort of a detour and look at stress analysis, which is more of an advanced topic in not just Inventor, but in engineering in general. And you as engineers will probably do stuff like this when you go out into industry. And so I want to kind of give you an idea and a flavor for how that works. Okay. Okay. So are there any questions on that? And did everybody get the attendance code? And did everybody get the handout for the wheel that I just passed out? Did anybody miss anything? Oh, one final thing I'll mention. So I have like a stack of handouts about yay thick in my office. I have copies of pretty much every handout that we've had this semester. Okay, including a few packets of the final assembly drawing and all that. Long story short, if you're missing anything, I'll probably bring that big stack on Wednesday, and if anybody's missing anything, grab it. But past that, I'm probably going to start getting rid of stuff because it's starting to get, the stack's starting to get pretty high. Okay, all right, so with that, let's go ahead and talk about our topic today, which is stress analysis, okay? So I'm using the term stress analysis because this is the term that Inventor uses. Inventor calls this process a stress analysis. general conceptual term for this is a finite element analysis. Okay, this is a computer-based method for doing structural analysis of complex systems, as it were. Okay, and I want to give you an idea of how this works. Now, I want to preface this by saying the actual theory and topics behind finite element analysis, I mean, this is grad school level stuff. This is pretty up there, okay? So really what we're focusing on today is just the software components of it. But just because the ideas of finite element analysis are pretty advanced doesn't mean that we can't learn something here in Inventor regarding the basics, okay? So I want to talk about what finite element analysis is. So what I have here is a screen capture of a representative finite element analysis. Forgive me, I'm a civil engineer, I can't help it. So this is a beam to column bracing connection in a building. And you can see this sort of rainbow colored plot. And this rainbow contoured plot is plotting the stresses in the beams and columns as it's being subjected to various forces, okay? But, so this is kind of like what finite element analysis looks like, but this isn't really what it is. What it is a computational technique that we use basically as a means of approximating or predicting the response of systems due to a series of external forces, right? So the idea in a finite element analysis is that we have a problem that's really complicated. It's usually three-dimensional, maybe non-linear response, like really out there stuff. And what we do is we break down that structure into a group of simpler regions. Okay? So if you look here at the image on the slide, you can see the I-beam and the column and the brace, that square brace and whatnot framing in. But if you look at it, you see this like net-looking plot over it. It looks like this grid of like triangles and squares. Does everybody kind of see that? Okay. So each one of those little blocks has a name, and we call it an element. Okay. And the idea is that in finite element analysis, we assume what the solution looks like over that little itty-bitty region called an element. And so we break the structure down into a bunch of elements. We then assemble those elements to simulate the whole system. And then we just do a lot of equation solving to predict the behavior. We basically, not to get too far down the rabbit hole, but we take a bunch of differential equations and turn them into a bunch of linear equations. And computers love to solve linear equations because they can do it darn quick, okay? So the first point I'll mention is that the accuracy of your finite element analysis is a function of how many elements that you use, okay? And we'll see that actually today, okay? Now, I've got a bunch of different engineers in here and a bunch of different applications, so I wanted to show you a couple of cool pictures of what you can do with FEA. You can do some really cool stuff. This image here on the left is actually a finite element model that I built. This is from my research group. We were looking at live load forces on highway bridges, and so we did a field test of a bridge. This bridge was in Iowa, and so what we did is we put a bunch of truckloads on the bridge, and we measured the response. We had experimental data, and then what we did is we ran a finite element analysis. We put the truck on the bridge, and we recorded the response, and we said we wanted to be able to compare the experimental data to the real world data, to the analytical data. And so this is a screen capture from one of the finite element models that I ran as part of my research. I have here on the top right, this is an image, this is a model of blood flow through the aortic valve. I took this from a faculty at MIT. This is some of their work, so you can do fluid flow work in finite element land. This image here on the bottom right is a thermodynamic. This is a heat transfer model looking at heat flow through a heat sink in a circuit board. So you can do a lot of like really cool stuff with FEA. And again, the idea with FEA is that you all as engineers are going to be learning the fundamentals, the theory. And don't get me wrong, you're going to use those fundamentals and this theory when you're solving real world problems. But when the geometry gets just really wild and gets really out there, a lot of times we'll just resort to something like this. The big thing about FEA is that FEA, by its nature, is approximate. Okay, it will not give you the exact perfect answer. It will. The idea, though, is that it will give you a close enough answer. Okay, and you'll kind of understand what that means today. Okay, in order to understand what's going on here, I do want to take a topic on the side and talk about some basic topics in mechanics. And I'm keeping it pretty basic because this will be relevant for our assignment that we're going to do this week. So I've got, again, some pretty pictures up here, and I'm just going to keep it simple, okay? So let me start off with a pretty basic scenario, okay? Let's say that I have two objects, okay? So up here on the screen, I have two objects. One of these objects is an aluminum soda can, okay? And the other is an aluminum billet, okay? So the idea is that we'll assume it's the same material, okay? It's the same material, just one's a soda can and one's a solid billet of aluminum. Now I think that I'm probably pretty strong enough to be able to crush that soda can in my hand. Does anybody think I'm going to be able to do that to that aluminum billet? No, right? Well, I don't understand. I mean, it's the same material, right? Are you all saying I'm not that strong? I know I'm a pretty physically intimidating guy, but that's a joke, not a very funny one. But in all seriousness, I'm not going to be able to do that with my bare hands. Okay? The reason is because of the object's geometry. So like to apply a little bit of math to the scenario, just to kind of like get your mind thinking about it. Let's say that I have some material, and let's say I take that material and I apply tension to it. And I say, I'm going to yank on it in tension until it fails. And let's just say that it fails at a load of, I don't know, 100 pounds. Okay? If I were to increase the size of the rod, would it fail at 100 pounds or would it fail at a different load? Like, let me put it like this. If I were to take that rod and double its size, how much load would cause the doubled rod to fail? If the first rod fails at 100 pounds and I take that rod and I double its size, how much will it hold before it fails? 200, right? Pretty straightforward, right? The idea is that if I take the rod, I double its size, I'm going to double its capacity. So far, so good? Okay. The reason is because of the rod's geometry. So a lot of times in mechanics, what we care about is not so much forces, but stresses, okay? So when you take a course in like statics and dynamics, you learn about forces, but then in mechanics of deformable bodies, you take those forces and you typically resolve them into stresses, okay? Now, you probably have not heard the term stress before, but you have probably heard the term pressure, okay? I imagine everybody here has heard the term pressure, okay? In engineering, we differentiate between stresses and pressures. Pressures are more related to fluids, things like liquids and gases, whereas stresses are related to solids, okay? So we're talking about solid bodies here, that's why we use the term stresses. And so the idea is that when we're looking at a given object, we're not really so concerned about its force, more as it is its stress, its force per unit area. So going back to the idea of the rod, if I took the rod and I tripled its size, it would take 300 pounds to fail it because it's the stress, not the force, that governs how much the element can hold up. Does that idea kind of make sense? Everybody kind of with me on that? Yeah. So if that's the case, let me throw another scenario at you. How about this? Okay, so let's say, okay, you're telling me that the size matters, that the geometry matters. Well, here I've got two scenarios. I've got aluminum rods and I have wooden dowels. Okay. Well, I tell you what, no, let's do this. Let's do steel rods and wooden dowels. Okay, so steel rods and wooden dowels, which have the exact same geometry, exact same diameter, exact same length. So these two elements obviously have the exact same strength, right? No, of course not, right? Why, right? Why? Because they're made of different materials, right? So in engineering, not only are we focused on the proper geometry to be able to withstand given forces and given demands, but we also have to ensure that we're using the proper materials. In other words, let's say I'm designing, let's go back to that initial rod that holds up 100 pounds. If I were to change the material, changing the material is going to change its capacity as well. And the question is, will the rod fail at 100 pounds? Will it be higher? Will it be lower? Well, it depends on what we change it to. If we have an aluminum rod and we change that rod to steel, it'll probably be able to hold up more. If we have that aluminum rod and we turn it into wood, it'll probably hold up less, okay? What we're talking about here in the business, we have a name for that. We call it a constitutive relationship. A constitutive relationship is related to the materials, the material behavior. In other words, like once we've removed the geometry, there's also the issue of what material we select. And different materials behave different ways. Wooden materials may want to split or crack. Alloy materials may want to bend or fracture. What about cementitious materials like concrete or ceramics? Maybe they want to crack or what have you. Understanding how the materials behave is crucial to accurately capturing both the behavior and being able to design. And so we're going to discuss that a little bit this week. The only other thing I wanted to comment on is the idea of a factor of safety. Has anybody heard of this term, a factor of safety, before? Has anybody heard of this? Okay. If you haven't, get used to it, because this is a fundamental tenet in the world of engineering, okay? So a factor of safety is the relationship between the amount of force that we put on a system and how much it can actually withstand. So I'll give you an example of a pretty basic scenario that I think you probably understand. How many of you all have ever been to Walmart or Lowe's or someplace like that and gotten one of those particle board bookshelves or desks or something that you put together in your dorm room or something like that? You don't talk about like entertainment centers, what have you. At least know what I'm talking about, right? Okay, so you put the thing together, let's say it's an entertainment center. You put the thing together, it's an entertainment center, it's got the little warning sticker up top. The little warning sticker says, don't put anything more than this much weight on the top, right? Okay, and so that number might be 200 pounds, right? Now, if I was a betting man, if I take that entertainment center and I take it on down to the structures lab and I put it under a certified hydraulic actuator and I increase the load until I break it, which is always a good day. Any day with controlled demolition is a good day. All right, if I take that entertainment center and I break it, I bet it can hold up more than 200 pounds. In other words, I bet that if I were to load that entertainment center, let's keep the math simple. Let's say it can actually hold up 400 pounds, right? So there is a difference between how much it can actually withstand, 400 pounds, and what we're allowing it to withstand, 200 pounds. Make sense? So what we can take is the ratio of those two and say that that entertainment center has a factor of safety of 2, right? And so a lot of times in engineering when we design to achieve target factors of safety. And those targeted factors of safety can vary dependent upon the industry. For example, if you're in the aerospace sector and you're designing, I don't know, satellites or spacecraft, you use relatively low factors of safety because the idea is you're only using that device once and it's real expensive to shoot something into space. So you have very tight design tolerances. So you might see factors of safety of 1 or 1.1 or 1.2. Whereas if you're designing retaining walls, because the soil properties are so variable, you might see factors of safety of 2 or 3 or what have you. So it just depends on the industry that you're in. So we're going to see both a little bit today. Everybody with me so far? Okay. Now, whenever you're conducting a finite element study, one of the first steps that you typically do is what's called a benchmark analysis. Now, the idea behind a benchmark analysis, especially if you're doing something from scratch, is look, I'm going to be modeling, let's say, some bracket in an engine component. I want to ensure that my modeling technique is going to work. Okay, so the idea is I will utilize that modeling technique on a well-defined problem, either a well-defined problem or maybe a problem for which I have experimental data, some way of comparing the results I get from a finite element analysis against some other established measure. I mean, keep in mind, these stress analyses that we perform using these computer-based methods are approximate, okay? So we want to ensure that they're accurate enough, okay? So what we're going to do is test out the modeling technique on this problem. This is a cantilever beam subjected to a uniformly distributed load or a pressure load at the top of the beam. This is one of the most fundamental problems in all of mechanics. And from an analytical or theoretical perspective, we can consider this problem solved. In other words, if you ask me for the deflection or the stresses or anything like that, I can give you the answer right now. Okay? In fact, So if I have this, so imagine this is sort of like a diving board, right? So if you stand on the edge of a diving board, the diving board will flex, it will bend, right? Okay. The maximum deflection, so if we look at how it deforms, it sort of deforms, I don't know, something kind of like that, like it sort of flexes like this, okay? And I propose that we can calculate this term here, which I'll call delta, okay? The amount in which it deforms. And my art will pale in comparison to what we're going to see here in Inventor here in a bit. Now, I can very easily compute this deflection using some basic mechanics. So if I use the terms for this beam is 25 millimeters wide, 20 millimeters tall, it's 200 millimeters long. I'm putting a 0.5 megapascal load on the top, and I need a material parameter. It's called Young's modulus. We use that the symbol E for that. Young's modulus changes depending upon the type of material that we use. So aluminum has a different Young's modulus than steel or copper or brass or what have you. Okay. So for the material that we're going to use today, aluminum 6061, E is about 69,000 megapascals. So if I plug and chug into a previously derived formula, I get that it deflects about 2.178 millimeters. Okay? So that's going to be sort of my target. I want to see if Inventor will spit out the same answer. Okay? And again, keep in mind, finite element analysis or stress analysis is an approximation. Okay? So let's see how it works. Okay? So what we're going to do is we're going to analyze this problem in Inventor. Okay? So let me pass around my little handout for this one too. So what I would do is open up Inventor and start a standard metric part. We're going to do metric today again. And one thing that is sort of worth mentioning is that we are going to assign a material to this part, and we're going to need to do that for our assembly as well.
We're making a new thing. Metric. Which one? Standard. The far right. Open AutoCAD. Adventure. Beam.
Okay. While that's passing around, I'm going to go to Inventor. I'm going to start a new part. Again, we're going to start a standard metric part, standard millimeter, and hit create. And I'm going to save this. We'll call it on the desktop. I'm just going to call it beam model. Okay. So this lecture is trying to focus on the stress analysis. So the part we're going to analyze is real darn simple. Okay. So again, all I'm going to do for creating this part is I'm going to draw a single rectangle on the XY plane. I'm going to dimension that rectangle to be 200 millimeters by 20. I'm going to finish that, and I'm going to extrude it 25 millimeters. And click the home button. Again, this part, I don't want this to be complicated. Just 200 by 20, extruded 25. Like, I'm just trying to get a rectangle, okay? A rectangular prism, I should say. Sorry. While everybody's working on this part, does everybody have both handouts, both for the wheel and what I just passed out? Everybody good? Okay.
Which way are we?
save my part. Again, save often, Control S, just save often. All right. Now, what we need to do now, well, I'm going to give everybody a second to create a part, and then I want everybody to follow up this part. Got most people creating this part. We're good, we're good. Okay, all right, so the next thing that we need to do, and this is a new operation, is to assign a material to it. Right now, we just created a part that's just made out of generic material. We don't need, there's no properties assigned to it. We need to tell Inventor that this is made of brass or copper or wood or what have you, or in the case of what we're talking about here, aluminum 6061. So what I'm going to do here is under Tools, I'm going to click Material. Looks like this checkered sphere type thing, checkered circle. Okay, let me make this a little bigger so everybody kind of see what's going on here. Okay, so we've got oodles and oodles of materials that are predefined in Inventor. Okay, I think I've got my mouse hovered over concrete, so that's why the beam looks different. Okay, let me move this over here. We've got a lot of different materials. By the way, everybody see here this first material, ABS plastic. Anybody know what ABS plastic is?
3D.
That's what you print with, right? That's common 3D printing material. Yeah, so one cool thing about Inventor is that if you're actually going to print something and then you want to see what that would be close. If you're wanting to print something and then actually see if it's going to hold up in a given assembly, you could actually analyze it here and see if the stresses are within what you want them to be. Okay. Now what we're going to do is click aluminum 6061. So down here for aluminum 6061, and then there's a little upward arrow right here. What I'm going to do is I'm going to click that and move it up. And what that does is that adds the material to the document, right? Now keep in mind, we can also create our own materials. For the purposes of this class, I'm just using the pre-built material library here in Inventor. But you can create your own and add all sorts of material properties to it, what have you. If you've done this correctly, the screen should look like this. There should be a generic and then an aluminum 6061 at the very top, and the aluminum should be bolder. Okay? What that means is that aluminum has been assigned to this part. So like what you can do is up here up top, you can say, okay, no, I want it to be generic, or no, I want it to be 6061. And you'll notice that as you're changing it, the beam goes from like gray to a lighter silver color, and that lighter silver color is aluminum. Okay, so this is you actually telling Inventor, no, this isn't just some random part, it's a part made of aluminum. Okay, now one of the things, you don't need to do anything here, but I do want to kind of show you something, and this is what I am showing you now is more for your benefit like next year or later in your engineering curriculum. If you click this little pencil icon over here next to aluminum, it brings up this little dialog box. And like, for example, if I go to physical, there's all of these properties that are defined inside Inventor for this given material. Okay. If yours is in US units, I can show you how to change that. Mine's here in metric. I'll show you how to change it to US units here, or to metric units here in a second. But if you'll notice, this library contains a lot of very fundamental properties for this material. I do not expect you as first-year engineering students to understand every one of these properties. You'll understand what these properties are by the time you graduate. But some of them should be familiar, like the density, and what have you. You should probably have an idea of what the density is. What we're going to focus on is this term called Young's modulus. Okay, Young's modulus is basically a ratio that defines the comparison between how much stress you put on something and how much it deforms on a percent basis. So the bigger Young's modulus is, the more stiff the material is, right? So like if you had a rubber band would help you Young's modulus would help you define the ratio between how much force you apply and how much it stretches and what have you. And so for aluminum, it's about 69,000, which is the value that was on that slide. This is where I got it. Okay. So I'm going to hit just cancel out of here. If yours is showing US units, if you go to this material browser, here on the very bottom left, there's a little folder and wrench icon. If you drop this down and hit set display units, you can change this to metric standard and hit OK. This is not changing any of the values inside the material library. It's just converting them to a unit system that you want to see. Okay, so I have here mine as metric standard. Okay. So I'm going to hit cancel here, hit OK, all this. So now I have a beam that is made of aluminum. Okay. So now I'm going to take this beam and I'm going to analyze it. Now the way that I'm going to do that is inside the 3D model tab, there's this little stress analysis button right here under simulation. Kind of looks like a rainbow, right? So we're going to click this stress analysis button and it brings up an analysis tab. Now right here, there's nothing here. There's no commands that we can use because we have to create a study to begin our model. So we're going to hit create study. Now, I'll just forewarn you, again, my purpose here in this lecture is to expose you to the basics of how this works in Inventor. But if we really wanted to go down the rabbit hole of how finite element analysis works, it's going to take a little while for us to arrive at the same level, like from a conceptual standpoint. I mean, like again, you don't start talking about the theory of finite element analysis until either you're a senior or maybe even a graduate student. So what I'll tell you is that we are using a lot of the default properties in Inventor, and that's perfectly fine for our purposes in here. But in order to understand a lot of this stuff, it just takes a little bit. So what I would just say is just bear with me. We're just going to use a lot of the basics here. But to give you kind of an idea of some of the things you can do, so here we can see, like, if you notice some of the options, we have a static analysis or a modal analysis. Modal analysis is more for things like vibration. So if you want to, if you have a structure that's subjected to a load like this, you know, you can determine its natural frequency and things like that, which is important for machine design. It's also important for earthquake engineering and what have you. For us, we're just going to use the basic options and click OK. And what that's going to do is now we've got some things we can do to the model. Okay, so in order to analyze this structure, we've got the geometry completely defined. We know what the beam looks like. We know it's made of aluminum. If we want to really define this problem, we really only need to do two things. That's fix it or constrain it. In other words, hold it in place somewhere. And the other is load it. Okay. So the first thing that we're going to do is a constraint. So if you look here at the very top here, there's a series of constraints. We have pin, fixed, what have you. We're going to do a fixed constraint. So we're going to click fixed right here. Now it's asking for a location. We're going to have to do a little bit of rotation here. We're going to rotate and we're going to click this left face of the beam. And if you do it correctly, you should see the little symbol pop up. That's a fixed constraint. Basically, a fixed constraint in mechanics will prevent that face from not only translating, but rotating as well, which is what we want. We want it restrained against translation and rotation. Then when that's all said and done, there's a little dialog box that pops up whenever you start the constraint command. You just hit apply, hit OK, or hit cancel. And then when we go back to the home screen, you can see that that constraint has been applied. You can see that that back face has been fixed. And the idea is that as we apply load, that face of the beam cannot move. The definition of a cantilever beam is one where one end is fixed. So that's why we're doing that. Okay? Now the only other thing we have to do from here is load the beam. So we're going to apply a pressure load. So if you look here up top under the loads, we're going to apply a pressure load. We're going to apply a pressure load to the very top of the beam. And the pressure load is going to be 0.5 megapascals. And when you hit OK, it should look something like this. And there's these gold arrows that show up indicating that we are applying a pressure to the top face of this structure. Okay. Everybody with me so far? So the only thing left to do is to actually analyze the structure. So I'm going to hit the little simulate button. Click the little simulate button. Click run. It chugs a little bit. And by golly gosh gee, we get a nice little pretty picture, right? That pretty picture has a lot of info associated with it, and we'll try to digest a little bit of that today. But this is our stress analysis here for this beam. If you notice here on the left, okay, let me drag this over, but here on the left, there's a lot of data over here on the left. We've got results, stress, displacement, etc. So essentially what Inventor is by default plotting are the stresses or those normalized forces inside the structure, but also the displacements, okay? So I'm going to double click the displacement icon here on the left, and you'll see the plot change. So let's do that. Okay. Now look what's happening. We've got a change in the plot, and what it's showing here is that on the left side of the beam, where the support is, the displacements are 0 because that was fixed. But then on the far end, the displacements are greater, right? We can see that the far end of the beam is red. What's the biggest displacement that we see here on the far end? What value are you all getting? I'm getting 2.165. Are you all getting that?
2.166.
Y'all getting that over here? 2.165? What did we calculate, by the way? 2.178? Maybe we can do better. Again, it's an approximation.
So I guess
I'm going to give everybody, how's everybody doing? Anybody have any questions?
the difference somewhere. Something like that. What are my settings?
Yeah, you're just viewing different results.
I did it at a different second.
Everybody good? Now, eyes up here, I want to show you something, okay? If you remember in finite element land, what we're doing is we're approximating the answer. The way that works is we approximate the answer over the elements. Now, if you click this little mesh view button on the top toolbar, what that will do is show you the elements, okay? The collection of elements, we have a name for that, we call it a mesh, you know? Kind of looks like a volleyball net, like a volleyball mesh across the structure, okay? Now, if you look here, we're not using that many elements. We're using a total of 110 elements to simulate the structure, which is a pretty low number. It is not that uncommon in the real world that you might have a system that has millions of elements. This happens all the time. So what I'm going to do is I'm going to see if I can do better with this answer. So what I'm going to do next to mesh view on the top, yes?
Is the number of elements random? Because I have 120, he has 110.
It can be dependent on how you created the geometry. So if you did something just a little bit different than him, it can change a little bit. It can change just a bit. So it shouldn't be, but yeah. All right, well, here's what I'm going to do. Next to this mesh view, there's a button called Mesh Settings. Okay. Now, if you click that, the Mesh Settings, it'll bring up a little dialog box, looks something about like this. And what it says is that the average element size is 0.1. So basically what Inventor does is it takes the geometry, it takes the average element size, and it sort of figures out the best mesh based on your target mesh size. I want better answers. So if I want better answers, I need more elements. So if I want more elements, I need to take this number and I need to make it smaller. Okay? So I'm going to take this 0.1 and I'm going to change it to 0.02. Okay? I'm going to hit OK. Now some of you might be thinking, well, nothing happened. That's true, nothing happened. Because in order to utilize this setting, I need to solve the structure again. So I hit the simulate button again. Hit run. Now look what happened. So now you can see there are many more elements that are utilized in the model. Here we can see we've used about 10,000 elements as opposed to 100 elements. But what's our maximum deflection here in the model? 2.178. That's a lot better, right? That's what we were expecting. We were expecting 2.178. Now, it required us to substantially increase the number of elements in the model to do that. So I guess the question for you as an engineer is what's close enough? What percent error are you going to tolerate in your modeling technique? That's kind of the idea, okay? And I got to show you a couple other things just because I can't help it. If you look here at the very top, there's a little button here called Animate. If you click the Animate button and hit play, I mean, come on, that's just cool. Okay, so animate the structure, and so this is sort of like as the load is being applied, you can visualize the deformations and whatnot. So as the structure is deforming, you can see that. Okay. So far, so good. You can also say, let's look at the von Mises stresses. Let me hit stop. Let's double click the von Mises stresses and let's do that. Von Mises, I'm not gonna, that's really getting into the, really getting down the rabbit hole on stresses, but von Mises is, best way of describing it is sort of like an average stress across the whole section. That is a woefully inadequate definition of what von Mises stresses are, but for our purposes it's close enough. And so you can see as you apply the load, the stresses increase near the support, right? Which would kind of make sense. I mean, imagine holding a ruler in your hand, tension it like this, then pressing the top. Your fingers are having to do a lot of the work, keeping it, fixed. That's what that's basically saying. The only other thing I want to show you here is if you look, so where are the largest stresses? Does everybody agree the largest stresses are at the support? So that's the worst case scenario for design. So if I hit OK, if you go down here on the right to the safety factor, I'm going to double check the safety factor. And what the safety factor is showing is where the worst case locations are for the purpose of design. Now, I really, really like this plot because if we look over here on the left, look what it shows here. It shows a rainbow contour, but it also shows a minimum, okay? What's the minimum factor of safety for this model? Shows here is what, 1.44? So that means that this structure is safe. In other words, the structure's capacity is larger than the loads it's being subjected to. So any time that factor of safety is larger than 1, the structure is safe. If the factor of safety was lower than 1, the structure would be unsafe. And so if the factor of safety was less than 1, you as the engineer would have to go, okay, do I need to use a different material? Do I need to make the beam deeper? Do I need to change some of the geometry to adequately withstand or resist these loads? And that, my friends, is engineering. That's what we're all about, okay? So again, we're doing this for a fairly basic problem today. What I'm going to do for you all on Wednesday, so the way Wednesday is going to work is I'm going to give you a little bit more of a difficult problem from a mechanics standpoint. We're going to look at a plate with a hole in it. If you look at a plate with a hole in it and you apply a lateral tangential load, the stresses are a lot cooler. They're a lot more challenging. And so what we're going to do is we're going to take that plate and we're going to test out a few different materials. And we're going to see, okay, is ABS plastic a reasonable material for this? Is steel a reasonable material? I'm going to have you all be engineers and decide which material should you use for this application and why. Okay? With that, ladies and gentlemen, that's all I have. I'm going to pull the QR code up one more time, and I will see you all on Wednesday.